Howdy.
Howdy.
Okay, first, welcome to our speaker series. Today we will have our distinguished professor from University of Iowa, Dr. Milan Sonka, to come here to give a talk on the interdisciplinary AI research is their recipe for success. And I'm Xingyue Ye, I'm a professor in urban planning and also with geography and computer science. I direct the Urban AI Lab through Data Science Institute, that's A&M. Every semester, each theme lab we will have a spot to invite a distinguished scholar from kind of other university to come here to give a talk. I have the great honor to invite Dr. Milan Sonka here through the introduction of Dr. Tianbao Yan of computer science. And if you have read the flyer of his talk, you will know Dr. Sonka is a well-known scholar on medical image processing. Certainly, it's only one of his achievements. Through that, he's a fellow of the National Academy of Inventors, IEEE fellow, and among many long list of honors. But at the same time, he is an AI education leader. He directs the Iowa Institute for Artificial Intelligence. For that one, is not only for medical imaging, because he is a co-director of Iowa Biomedical Engineering Center. And for this Iowa Institute for AI, he promotes a cross-campus collaboration, not only between the engineering and with other engineering, or with medical school. Additionally, he also works with social science humanities. So in other words, especially this is important nowadays, since after the ChatGPT, and more people in common public understand the power of AI. So I think now is a critical time. Scholars on campus, not only faculty, staff, students, begin to realize we really need to work together to deal with many challenging problems through the power of AI and the domain knowledge. Without further ado, it's your time.
Well, thank you very much for a very kind introduction. Thanks a lot, and it's a pleasure to be here, of course. As you already heard, we put together this initiative for AI to help bridge the people who have data and may not have the AI knowledge, and people who have the AI knowledge and may not have the data, or they don't understand the specific problem. But it's also interesting to look a little bit in the past, because one thing one thing which is interesting on artificial intelligence, it's actually not a new thing. And as Edo just said, it may look like AI just arrived with ChatGPT, but it's actually not the case. If you look back, it's really an 80-year-old thing, which many of the principles were spelled out in Alan Turing's 1947 lecture and his 1948 Intelligent Machinery Report, where he described how the computers can learn from experience, even at that time, which is quite remarkable. And he came up with the idea of the artificial neurons, which looked like that, and for all of us, it's very much similar to what we know. There was some input, some weights, some firing threshold, or something like that. That was followed by an Adeline that was, it came up to existence in 1960. It's an example of the original Adeline knobbing, because it had many knobs, but you were able to set different weights, and it was really an analog computer that was able to determine, based on many inputs, whether the answer is yes or no, based on the voltmeter output here. Followed by the perceptron in 1969, and neural networks in the 70s and 80s, and deep neural networks coming after that, as we all know. And interestingly enough, as many things in science, failures and successes are intertwined, and there were periods of big promises and periods of previous appointments. So in the 1950s, the area was really flooded by funding. It was a great time for machine intelligence research at that time, and they were promising. People were promising that human-like intelligence will exist in 2 decades, which of course we know didn't happen. The problem was shown to be much harder, and the period of good funding, resulted in the funding drop after that, and again, we already understand that because researchers and people at the time did not have enough data available. They did not have enough memory on those computers at the time. They did not have enough sufficient computing power. But this is something what I really would like you to get from this talk is that the principles which we are following today, most of them are known at the time. They did not change that much today. So we got access to big data, we got access to increased CPU and GPU power, much bigger memory and storage, World Wide Web with all the data and information available there. So we are in a great period for us in the new AI hype. And there is some promise that actually go home. I think that we are getting to the point that things actually can go. So what do we expect from there? We really expect a substantial societal industry. We expect many things to happen. Research, all aspects of our research endeavor. We are mostly talking about research. Society is in the rush. And deep learning is the decision making is that smart system will start appearing. Large language generated models are here. And no matter how you look at that, you have to learn from the data. And we need the data and we need the truth to learn. And now the question of the truth, now it's debatable what exactly you need, and you already talked about this down about that. You can learn without the truth to some extent, and then you can infuse the truth later. But one way or the other, the truth must be there because otherwise we cannot finish that. And now this will show, how many decades of experience I have. When I started my PhD in 1980, I was reading this book, which is Czech, and was by 4 great guys. One of them, Jelinek, is the one who brought to Honeywell the adaptive thermostats of self-learning thermostat. If you remember, the first one, which was able to predict how to start heating based on the temperature outside and how to learn parameters of buildings and how quickly they can heat up and all those things. But he was in my department in Prague at the time before I was talking about some simple classification problem based on linear classifier, and I was very happy about whatever correctness performance that I had. It was in the healthcare problem. I was saying, this will help the patient because they were known, that these guys will remain healthy and this will run. Of course, this guy told me, we don't know who is misdiagnosed because you don't have 100% correctness, right? Who is that? That sort of stayed with me, and caution is needed, and also drove my interest in the knowledge-based medical image analysis, which gets me to one of the precursors of the AI initiative which we have. And in 2007, we formally created an Iowa Institute for Biomedical Imaging, and I was co-directing that, and still co-directing it with one MD, was from the College of Medicine, and the institute itself reported jointly to the Deans of Engineering and Business. And that was something what was quite interesting because if you ever work with physicians, you know that they have their specific set of egos, and just letting engineers to be equally partnering in something what has medical in its name is already an accomplishment, and we built a way from that. And the IIBI, the Iowa Institute for Biomedical Imaging, really was trying to become a university-wide resource that facilitated integration of interdisciplinary biomedical imaging research. And we also wanted to have, good resources, and we were able to convince the central administration that this is an important part for the university, and the hospital is a big part of the University of Iowa. And so they built this building for biomedical imaging research, where we have 2 floors in this building that are 100% research-oriented imaging. And we have something what, before this was built, we were able to image our research subjects or research animals like at 4 o'clock in the morning on the clinical scanners with all the cleaning before and after and all those things. So now we have a substantial space and also substantial environment with like 2 to 3 Tesla MR scanners for research only, PET CT scanner, MR Linux scanner is going to be there. Really fantastic facility for imaging research. And the reason why I'm talking about that is that it really enabled us to start having more and more experience with interdisciplinary research that involved people who initially, when they met or when we met, we did not understand each other. We were talking medicine, we were talking image analysis, and it went on. And because it really started in 1990 and resulted in the institute, we learned that the interdisciplinary teams really need time to understand each other. And we started to have NIH projects, and we started to be successful in that. And we developed that mutual relationship where we engineers had NIH grants with physicians being on it. We were PIs, they were PIs with us being on it. And we realized that we needed each other sort of equally. And that's one of the differences in Iowa compared to many other places where imaging is actually embedded in radiology. And the imaging people are sometimes viewed as, technicians on steroids. So we were very careful about it. And so we learned about how to make things work across disciplines and how to be equal partners with them. And just a sidetrack here, we worked on experience-based, example-based machine learning for medical imaging very early on, and we actually published the first paper with the name, Learning for Image Analysis from Examples in the late 1990s. So based on all that experience, we understood 5, 6, 7 years ago that a change from biostatistic to artificial intelligence and machine learning approaches is coming. And we predicted at the time that to secure future funding, especially for the successful groups on campus that did variety of research and usually use biostatistical or statistical approaches, that we must change because the funding agency will expect something different than just statistical analysis and associations and p-values. And so we were able to convince people that we need to modify the ways how we are doing things, and that the future success of Iowa really depends on providing the AI machine learning expertise to the groups that have data and have the needs to do the analysis, but may not have the AI machine learning expertise. And as I said, we were able to convince the central administration to give us a little bit of money and start became the Iowa Initiative Partner. So it has that little bit of history and how we got there, which I think is important to understand, because we didn't start from scratch. We started with very deep relationship with healthcare, being public health and medicine, this understanding what works and what doesn't, and being able to convince the central administration that we can broaden it to other areas. And this is another important part, that at least for now, those researchers who have the data and have the problem that needs to be solved are typically not the same ones who are educated in AI approaches. Which means that you have to bring those two groups together. And once you do that, the domain experts typically do not immediately understand the AI experts. And the experts, of course, are not experts in the domain. And so that needs to develop. Which gets back to what I said before, takes time before the team members actually understand. But the main message is that the AI know-how must become available to IM research teams, our research teams, and the mutual collaboration among them. And so we officially created this initiative in 2019, just before COVID, hit, with the goal of enabling new endeavors by providing collaboration services, by experts in AI, and also by creating environment for people meeting and so on. We built two beautiful labs, one in business college, one in engineering. You envision that people will be meeting there, sitting next to each other and solving problems and talking and discussing. That never. Because about a month after it opened, it immediately closed for several years, and people were not sitting next to each other and breathing on each other and so on. But regardless, we did have the goal of centralized, universal access to collaborations, facilities, students annihilated. And the entire motivation was that it will all help us write better proposals and get more extramural funding. And it still is behind what we are doing as a major issue. So the AI initiative, to make something like that happen, really needed a longer-term funding and dedicated staff. We can talk, why I don't say dedicated faculty. I think it needs to be staff. We got 3 years of central funding, not much money, but some money, that allowed us to hire 2 AI machine learning experts, allowed me to get some course release so that I can concentrate on this from the College of Engineering, not from the Central Administration. And we got into agreements with different colleges and departments. We got their level funding based on separate memoranda of understanding. Writing domain-specific calls for proposals. Meaning that we can go to the Department of Psychiatry. Psychiatry gives us a little bit of money for some number of projects, like 2 projects a year. And we go to their faculty and say, what kind of problems do you have? What kind of data do you have? What kind of need do you have? And if it all matches, things may materialize and eventually go to large event submissions. And the interesting thing for somebody who did medical imaging was that we started to work with projects which had very broad coverage and were exciting because they were. And so we collaborated with College of Medicine, College of Liberal Arts and Sciences, Business, College of Engineering, Education, Nursing, Law, and departments of Psychiatry, Radiology, Biochemistry, Ophthalmology, Cancer Center, this Public Health Injury Prevention Center. So just from the collaboration partners, you can see that the problems are probably going to be pretty well. So the question was, who is going to do the work? Somebody needed to develop things. And so we started with a data scientist, which had a limited machine learning experience, later left and became assistant professor at the college in New York. We had a master and PhD student. The master students eventually graduated and became staff. That's actually one of the 2 people I had. And I also hired a PhD staff person, postdoc at the time, with mostly image data, medical imaging data, and medical record data experience. And these people are, from the beginning, have about 10 projects each to work on in collaboration. So they put about 10% of their FTE time to each project they work on. So the current collaboration model is that we have those memoranda of understanding. The unit pays about 15 to 20K, so something that virtually any unit can afford. And we write and send a call for proposal. And it's unit specific. So it's tailored slightly to the needs of the individual unit. The calls for papers, calls for proposals are sent to the unit's faculty or research staff. They submit a letter of intent where they describe the problem, describe the data they have. And we talk to them and we help them shape up the proposal. So we share the proposal with them, making sure it's actually feasible. They write a 2-page proposal, simple, and that's being reviewed. And we typically have twice as many proposals than we can fund. So there is some limited competition enough for this thing. Reviewed, and the expectation is that they submit a larger extramural grant within a year after this being. So, for example, for the liberal arts and sciences, the call for proposals, we tell them that for your proposal to be responsive, it needs to address important interdisciplinary question using data-driven approach. If they say, I will use statistics, that's not what we do, right? Go to the statistical call. Nothing wrong with that, but no else. It must be based on sufficient data to answer or frequently start answering such questions. If you have 10 cases, that's probably not sufficient there. They need to need the machine learning expertise from us as an enabling strategy. If they are already experts, we cannot help them with much. They have to describe what they want to predict or classify, what are the outcome variables, and what are the data they are going to use for that prediction. So, for example, we aim to use social media-based data from subjects, which is the input, to predict their behavior and lifestyle choices, which is the output. Or we aim to use information about air pollution sources, weather forecast, atmospheric airflow data, and the inputs, to predict location-specific air pollution. So, in that call for proposals, we already try to set it up that you need to have the data and you need to know what they are trying to do. And they must be willing to invest effort into building a unit interdisciplinary team. I mentioned that we asked that unit to give us some money. Not a single dollar goes to the PI. They have to invest. They have to say, I'm going to get the expertise from IIAI. I will work with them regularly. As a result, my payback is not the money from this. My payback is that I will have enough good-looking pilot results so that I can write a bigger program, which they otherwise could. And that larger extramural funded proposal plan must be included in the 2-page. So just to understand, this is how the timeline worked, and this is for the most recent thing. And someday they just email a brief statement of intent, just title, aims, and date. After that, within about a week or 10 days, we meet with each of the proposal teams and we discuss the proposal. And we shape up the proposal. We tell them, this is not going to work. Your data, we don't have enough data. What else can we do? It sometimes changes. We have about 2 weeks to submit a proposal after that. Then we have a week to review it, and off we go. So today or tomorrow, I have to send those announcements. This is roughly how it looks, and it goes to different departments. It's little differently worded, and so. So, what are the examples of those individual projects which we work? And I was trying to start with something what would be hopefully a good project that we can talk about in this group. So you were talking in the morning when we met about digital twins. So we had one pilot project with 2 environmental science researchers about developing a digital twin model for predicting microtoxins in our labs. So the goal was to construct a deep learning model for prediction of NO2 concentration, which were the output from emission, mobility, land use, meteorological observation data. And the inputs were coming from MERA2 data, which probably many of you are familiar with. I'm not really. But it uses air temperature, detailed air temperature information, surface pressure information, detailed wind speed information, aerosol optical depth information, humidity, particle concentration, precipitation information, bias corrected, and molecular boundary and high because now, so that's the input, right? That's what we are trying to use for determining the nitric oxide concentration. Now we need something, some truth to learn from. So the truth is coming from a tropospheric monitoring instrument. It's a satellite instrument that is able to get the NO2 concentrations. However, number one, the TROPOMAY data are not full. They are missing something. So they have the white spots where no data are there. That's one problem. The second problem is that the MERA2 and the TROPOMAY data are different scales, so needed to be adjusted, stitched in order to do something. But there is a lot of data available, which is good and which was much. And as a pilot project, what we did for them was that we created an approach which was really a combination of generator discriminator, the adversarial network, where the generator was a unit-based image analysis-based approach, because it started with image maps of the MERA information stacked based on individual features as inputs, and the outputs was the concentration of nitric oxide in the same image. And the outcome, as well as the generator loss, was calculated for those non-empty, non-white. And the discriminator was part of the convolutional neural network for training, where we're looking at the real output part, that would be the real nitric oxide plus the MERA image maps, and the generated part was stacked MERA image map and generate the predicted nitric oxide. And so in the training, you are trying to mimic the original NO2 prediction here, and the discriminator is trying to find the difference between the real and generated output and combine with the adversarial map. Here's an example how it looks, and we use 85% for training, 50% of data for testing. And these are the predicted information corresponding to truth. So I don't know how much you can see, but hopefully you can see that for example, here it roughly agrees that we have that predicted greenish spot here, or the greenish spot here, the line here, and so on. So the prediction roughly agrees. This is on training day, okay, just showing how that worked on the training day. If you put it on testing data, and this is the input, this is on the output here. And the output is able to fill those white dots, the missing data information. How well? Well, we don't know. We have no tools for comparison. But overall, the R-square score was about 0.28. Is it something to write home about? Well, it's a question. It's something. It's not zero. Can it be better? Sure. Is it enough as the feasibility proof to write the NSF grant? It was. And so, as I said, we are not at the point where we are trying to answer the problem. We cannot do it for the amount of money. But we can demonstrate the feasibility so that people can write it. That's the goal of the Another project which may be interesting to talk about is flood forecasting and control. And, this particular project is motivated by our collaboration with the Iowa Institute for Hydrologic Research, where they were trying to develop a way how, instead of building one big dam, is to put several smaller dams in the entire watershed, and and find out how you can catch the water appropriately and what to do and how to plan. And so the questions which they need to answer is how many reservoirs would be needed to achieve comparable risk reduction levels as if you have one big one. The motivation is that building several smaller ones is actually much less expensive than building one big one. Has a different environmental impact. And where should they be placed? That planning requires an estimate of water outflow at various cross sections of the river. And those outflows are calculated using mathematical models and based on mass transport and mass conservation equations. It's computationally intensive and they, it takes time and don't quite get the results in the group. So one of the problems along this entire journey of having this design being done is a need for fast estimate of location specific outflows. This is how the test watershed looks like. This is the Mississippi River, part of eastern Iowa. And they have multiple locations with US Geological Survey gauges that are able to determine the water flow in those areas. So the first question as part of this entire work, the feasibility part of this work, was given those information from the cross-sectional stream flows at those specific locations, can we determine the flow of water in any of those locations in some number of hours, right? Based on precipitation, based on how it all looks, based on train data. And the train data are difficult to come across, but you can simulate this. And so they use the mathematical equation-based simulation for 5,000 different events, and they simulate the precipitation for every 1 hour time point, and they calculated, generated the stream flow at all locations in the river for every 1 hour. And so they generated, with a lot of computational effort, about 2.5 million data points of 5,000 different events. We used 80-20 splits to train the university. And that data was what we got. And well, let's see how different models work. And we created one model based on the long short-term memory, combining the molecular perceptron here. Another model was very similar. However, it included the first one included that 24-hour stream flow of the current link. The second was not including that. Then there was a model that used the rainfall only, based on a gated recurrent unit networks. Another model, rainfall and upstream data. Another model was the attention model. So different combination of things how we can use. Details are not important, but whatever we are able to get from the input. The results were assessed based on the quick uptime efficiency modeling, and because the concentration time, the time for the right differs to the watershed, we were using some normalized. And again, the NSF project was submitted as a result. Here's an example how those individual models work. So here are those individual events shown in different colors here. And here is the 24-hour prediction of the true outflow data. So the true outflow data are in black, you cannot see it too well. But you can see that some of the models perform better than the others. That, for example, this model 2 is sort of underestimating the peak, which is important, right? That's what determines the plot stage and the plot level. But the others were doing much better. Some of them didn't have quite the timing right. Some of them were doing okay. And but perhaps most importantly, if we compare the overall accuracy, we compare that with a sort of simple persistence model that sort of says, what we see now is what we get an hour later and 2 hours later and so on. We are able to have much longer lead times using our models than using the naive approaches which are still being used based on. And so the models don't fall apart as quickly as it does. And as I already said, also enough to write another project that came up from collaboration with physics was the development of the electronic nose for detecting, identifying multiple volatile organic compound VOCs that had high spectral. And so the first question was to determine the percent concentrations of elementary VOCs in some synthetic spectra of mixtures. These are the VOCs which we are looking at. And the second was determine the presence of specific bacteria in mixtures, because those specific bacteria actually emit some signature VOCs. And again, the work was based mostly on the syntactic data set. And generated either for 3 to 10 or 3 to 5 micrometer lengths. 1.5 million samples, so large enough data were generated artificially with the mixed spectra of those 7 gases. And because you generated all synthetically, then you know what the true concentration is. And so able to predict the proportions, you also looked at the probabilities of 3 bacterial classes, either mixed or E. coli or peer reviewers. So for the first stage for the mixtures, the goal really was, this would be the reality where you have the spectrometer trying to get the spectra. We have the synthetic spectra here running through the GRU network, and we are able to predict the percentages of individual of the 7 VOCs which we trained. The molecular perceptron approach was used for the detection of the presence of one bacteria, second bacteria, and both of them. We were surprised by the high level of performance we achieved. And so we got very close to 1 R² in this particular case, better for the more narrow spectral data set. It's a smaller routine square between the decisions of the different percentages. For the 3 bacteria classes, again, excellent accuracy, excellent spot. So something was demonstrated the promise that this approach can actually work for detecting compositions of VOCs. And 2 projects were submitted, one for NSF and one for DOT, based on that. Because this is something how you can potentially use for detecting dangerous substances, dangerous gases. One thing which I would like to show is one project which gets to. This is an interesting project which I shouldn't claim ownership, I do not claim ownership of. But it has some consequences for the AI imaging initiative that is some other projects. So what this is Dina, and Dina, interestingly enough, is a Department of Intelligence Bureau advisor, but it's also the first name of the Technical Computer Engineering Secretary, long-term secretary who always answer the questions to the students, whoever came, answer these questions about which class should I take and what is this and what is that. And so the department, with help of one of our colleagues, created an advising system based on ChatGPT. And we can start asking questions like, if you go to an advising session, what courses should I take to study, what do you want to study in electrical engineering? AI. And it's not super fast. And it's not that surprising, what you will see in the end. You expect a reasonable answer. What is sort of interesting here is that it actually uses the local electrical and computer engineering dialogue information which is available on the website. So calls the information which is ECU specific, and gives you, the answer. It's going to start somewhere here. The focus on artificial intelligence in your study, you should consider taking the following courses. And it gives you sort of the list of things which you otherwise get from talking to an advisor or searching, the mix of web pages. And questions I want next. I don't know what's going to come. So this is actually becoming a good hit for our students, and also becoming a good test example what our departments can do, because it frees up, our faculty from answering those repetitive standard questions. And in this case, after you identify the courses, check the prerequisites, and that consult the academic environment, whatever it says. So this is something what is currently alive for ECE and being used and so on. As I said, this is not something what covered in the scene, but it's covered in the screen. So I would love to show you the patient education thing which resulted from that. The Department of Internal Medicine came up to us and said, we have a problem, and our patients are repeatedly asking the same questions if they go to have the atrial fibrillation and the procedure. And so, can we develop something that would use the ChatGPT because it's PDP, because it seems to be really good in answering many other things? Can we give them the tablet so that they can ask all those questions before they talk to the physician, because the physician's time is precious? They always ask, should I be scared? What should I do? And what is the progress and how is the procedure? So we are developing, we actually have developed in about a day and a half a system for patient education in preparation. And very simple. Well, actually, others work on that. All what you do, you take the same interface which we had for DINA already in place. We just feed it, instead of electrical and computer engineering documents about advising, we feed it with internal medicine documents about integration, and off you go and start being, giving meaningful answers. And this works for us because in both cases, the advising as well as in in this patient education, we are not providing any patient-specific information to the AI. We do that, and it's reasonably straightforward, and the data really exists on the web. So it can be done very quickly. And, it's currently being tested by the physicians. There is something that we can let others do. There are many other non-medical examples, but we don't have time for all of that. Let me just show you one medical healthcare example. So a question which is a very important one. If somebody with cancer gets an X-ray CT image, pre-treatment at time 0, And then they are put on some chemotherapy drug, and they get CT images 3 months later and 6 months later as a follow-up. And physicians, at the time of the second follow-up, determine whether the chemotherapy drug is working or not, or whether they need to be switched to a different. And the question which we asked, physicians asked, was, can we actually derive the outcome already at time 1? And if the drug is going to work in the future, let's keep them on the drug. But if it's not going to work, let's switch them to a different drug. Because otherwise the tumor happily keeps growing, and that's not what we want to see. And the success here was the 20% decrease of volume of the tumor between the pre-treatment volume and the second follow-up volume. That was considered a responding feature. And here comes the cross-pollination with the Biomedical Imaging Institute. We already had a way how to identify tumors. And so these are metastatic melanoma tumors, in the lung or in the outside region over here. And we had a way how to determine them, detect them, how to segment them, how to get radiomic features out of them. And we are able to use those radiomic features to train a predictive mechanism for determining which tumor the treatment will work and will good. Out of the 52 lesions, a relatively small number, we had 34 that responded to treatment. We couldn't use any deep learning for that number, but we used random forest in this case. And we're trying to predict the outcome from the baseline and time 1 scans. We used threefold cross-validation because it was small. And it was promising. We were able to get overall prediction accuracy response by 55%. We were better for just identifying lesions that do respond to treatment. Again, as I said, in the slides 4 or 5, we don't know which ones. But overall, this looks very promising, right? And interestingly enough, and that's sometimes the tumor, if it's treated, enlarges in time 1. But it's because of inflammation, it's not because of the real growth. And the radiomic features which you are using were able to 100% correctly predict the responsive, non-responsive case, even for those 13 lesions that actually increase substantially in size, and distinguish between the inflammation growth or the tumor growth, which is nice. And so there is an NIH submission. We can talk about some of the other things, how to determine acute kidney injury happening in 24 or 48 hours, how to identify patients with syncope. Should they be sent home when they come to the emergency department? Is an episode of fainting, or should they be admitted, and so on. Can AI predict extubation success in neonate, in very small sick kids that are put on a ventilator? You don't want to keep them on the ventilator for too long. And the physicians don't have a very good thing. So very different thing which you can talk about any of those a little bit more. And if you would like to learn a little bit more about those, you can actually go to the web page and see all the projects and click on those that have been completed and see the results and see the final reports. So you can certainly do it. But up till now, we worked on about 80 different pilot projects with those staff of 2 people. Occasionally somebody else involved. About 60 were completed, about 20 are active. This is the web page which gets you the details. What enables us to do that? Well, clearly we need power provider. We have an access to the high performance computing cluster with our large centrally managed and an excellent resource, which has GPU capabilities in some of the nodes. And it also has recently a HIPAA compliant storage, data access and servers, so that you can actually work with the patient information on that. And the hardware collaboration with the Imaging Institute is important as well, because we have some very powerful machines with super large GPU memory in the imaging part of the world, and if we need them for the AI part of the world, we can use them. Data access, again, is very important. And, for healthcare stuff, we have imaging-based de-identification pipeline in place. We have, IRB things in place. We know how to do it. We are not doing DoD, Department of Defense projects as part of AI at all. So that helps. And data are mostly benign. So what is critical for something like that, what I'm describing, to succeed? I think the central support is critical, as well as the support from individual collaborating colleges, departments, and research. The industry ties are important. We don't have them. We have some collaboration with NVIDIA, but it's sort of wishy-washy. But we don't have much industry around us. That's one of the problems. I think it's much better here. We need, and this is super critical, we need AI experts who are interested to solve diverse pilot problems. And I mentioned that those are staff people. They cannot be faculty in my view. The reason why they cannot be faculty is that faculty have different reasons to do what they do. Their objective function is different. They are optimizing a different set of conditions. They need to write papers, they need to write grants, they need to be successful themselves. These experts need to live to make others successful. And that's sort of why I think we need to be motivated staff people interested in that. And they need to be plugged into subsequent funded projects with motivation. We have to have a functional pipeline of calls for proposals, proper selection of projects based on true availability of data. If the data is not available, the project is doomed to fail. Project completion, start grant writing, larger project environments. And we also saw that some of the successful AI people are leaving Iowa, right? And so, it's part of the good thing probably that good AI people are in high demand because of it. So in the next steps, we are trying to convince now the Iowa Central Administration that we need to do more, that they have to put more money in that, so that we can concentrate on the work, that we can work with students and their experiential learning, that we can embed the students in those projects. That will decrease the efficiency of the AI experts, because they will also have to push the students. That's why we need some additional support. But it will result in a new pool of research assistants to support future research and potentially new staff. That can be. And we need to educate the new pool of researchers across the staff levels, develop a coherent set of workshops and courses. So in conclusion here, the IAI projects we started in 2020, about 20 projects a year, with 2 staff people and myself. A topical project specific expertise is sometimes, if you need to virtual reality visualization, we go to the virtual reality expert and helps us on these things. About 30 submitted grant proposals from the 60 submitted pilot projects, about 1,200 funded. And none of these proposals would exist without AI initiative, and this is something that I think makes us all happy and gives us good enough ammunition to actually go to the central administration. You should support us more. If you don't, you will not be as successful as users. Any questions I can answer?